And what I'd like to start with you guys is let's just go back to the good old unit circle. All right, and remember, guys, when we introduced the unit circle, the reason why we brought in the unit circle was so important because it really helped us evaluate trigonometric functions. For instance, when I said, what is the cosine of pi over 6, you guys didn't draw a triangle, use special right triangles, and then do adjacent over hypotenuse, right? We know that when we have a point on the unit circle, even though that is a special right triangle, but what we figured out was that's the x and the y coordinate. The hypotenuse was 1. I didn't need to use adjacent over hypotenuse. I could just figure out what that coordinate point was based on the special right triangle. And therefore, the cosine of pi over 6 was square root of 3 over 2. And we could do that rather quickly, right? So the unit circle was helpful for us. And so what we did is we came up with these basic kind of formulas, like the sine of theta is y. Cosine of theta is x. Tangent of theta is y over x. And again, we sometimes got confused with these because sometimes when I'd give you a coordinate point and evaluate 6 trigonometric functions, we would forget that if it's not on the unit circle, we had to create a triangle and do it, right? This is only for points that lie on the unit circle. Do these definitions work? And then we had cosecant of theta is 1 over y. Secant of theta equals 1 over x. And then the cotangent of theta equals x over y. OK? So what we're going to do is we're going to work into some new definitions for our 6 trigonometric functions. And our definitions of our 6 trigonometric functions, what we're going to try to do is only use the 6 trigonometric functions, not think about them in terms of x and y's as opposite over adjacent, or sides of a triangle, or as far as coordinate points on the unit circle. We're going to try to think of them in only terms of the trigonometric functions. So I'll give you an example, and then I'd like you guys to just try to see if you guys can come up with the rest of them. So the first one, let's just think of tan. Now, obviously, guys, if sine of theta is equal to y, that means y is equal to sine of theta, right? I mean, it's a reciprocal relationship, one to the other. So therefore, if tangent is y over x, doesn't it make sense then we could rewrite tangent as sine of theta over cosine of theta? Right? I mean, that's not like groundbreaking kind of thing. Like, it makes sense, right? So what I'd like you guys to do is see if you can figure out the rest of these, how else we could represent these. And my recommendation for you guys would be to start on the right-hand side and then try to see if you can work on the left-hand side. OK? So I'll just give you guys like 30 seconds just to kind of think about those. And then I'll kind of give you the answers for the rest of those. Let's see here. Let's do this. Oops, crap. Got to run out of room. All right. Can we go with cotangent and start? That's pretty basic, right? We could say that's just going to be cosine of theta over sine of theta. Now, I wrote cotangent and tangent twice, which might be a little confusing. So let's skip over the other ones real quick. And let's just look at cosecant. Cosecant's 1 over y, so I could say that's 1 over sine of theta. And secant is 1 over cosine of theta. So hopefully at least got to this point. And if maybe you made the connection to the next ones, that's awesome. Some people I know will not go ahead and get to them. It's a little bit more confusing. So what we need to understand then is think about, to figure out these, it's going to help you to, again, understand the relationship of your function and its reciprocal. Sine is the reciprocal of cosecant. What that also means is cosecant is the reciprocal of sine. So if cosecant can be represented as 1 over sine of theta, that means sine of theta can also be represented as 1 over cosecant of theta. And we could do the same thing with cosine. And therefore, even though we can write tangent as sine over cosine, we also understand that tangent and cotangent are reciprocals of each other, right? So we could represent this as the same way, 1 over cotangent of theta and 1 over tangent of theta. So these, ladies and gentlemen, are what we call the reciprocal identities. Okay? And what I mean by an identity, and we'll talk more about this next year when we get back. But basically, an identity is one side is equal to the other side, and you guys can see that basically these are true. Then these are just what we call our quotient identities. Okay? So from the unit circle, we can quickly kind of draw these up. And these are some of our most basic identities that you guys will make sure you need to know. All right? So again, I am now exposing to 8 identities, and we're going to add more. But these identities, these should be reflexes. You guys should know these very, very well. And again, we'll be doing so many example problems that I feel confident you guys will need to know these. You're not going to have to do flashcards and memorize these or so on. We're going to be practicing these quite a bit. Now, again, let's look at this unit circle. We think, well, what else can we come up with the unit circle that would obviously go ahead and, what else can we come up from this unit circle that we understand, right? And we notice that the unit circle, that triangle, is a right triangle, right? So besides evaluating the 6 trigonometric functions, what else can we draw from a right triangle? Starts with a P and rhymes with Pythagorean. Pythagorean theorem, right? If we were to do this, can we say x squared plus y squared equals 1? There's nothing wrong with that, right? So now, using our identities that we kind of create, well, not even our identities, but using our understanding of sine, cosine, tangent in terms of x and y's, we could also rewrite this as cosine of x squared plus sine of x squared equals 1. Now, notice how I'm writing that, and you're more than likely not going to see it written like that. Okay? So, and we'll talk a little bit more about this as well, but the correct form that you're going to see on tests and quizzes on homework would be written like this: cosine squared of x plus sine squared of x equals 1. Okay? So we're going to put the 2 right there. And we just got to be careful and why it's in there. And I'll make sure I address that here at the end. Now, so far, if you guys are looking at these identities, all of our identities have included all the 6 trigonometric functions, right? So right now, the Pythagorean theorem only involves sine and cosine. So can we rewrite the Pythagorean theorem in terms of cotangent, tangent, secant, and cosecant? And there's actually some fun ways we could actually manipulate this to do that. To save ourselves some time, what I'm going to do is I'm just going to show you a quick way that we can quickly find the other identities. First way would just be to divide by the sine. Oops. Did I do these all as thetas? Sorry, I want to write this in terms of thetas. I don't want to confuse the x's. You could do them with x's, that's fine, but I just don't want to confuse x's with these x's. So what if we divided everything by theta? Now, again, we have to first ask ourselves, is that a mathematical operation that's allowed? Are we able to divide or multiply an equation, everything by the same number? Yeah, remember rational functions? Remember, that's what we did. We multiplied everything by the LCD, right, to eliminate the denominator so we could solve. So yeah, you can go ahead and divide everything by sine squared. And if you do that, you get cosine squared of theta over sine squared of theta. Well, if cosine over sine is cotangent, then cosine squared over sine squared would just be cotangent squared of theta plus sine squared of theta over sine squared of theta. Those are the same quantity, so that's just going to equal 1. And then 1 over sine of theta would just be 1 over sine squared of theta would be cosecant squared of theta. So that's your other Pythagorean identity. And then rather than doing the same math one more time, what if we replace sine with cosine? Then we'd have 1 plus sine over cosine would be tangent squared of theta equals 1 over cosine would be secant squared of theta. So those are your 3 Pythagorean theorems. All right, so these are what we call our Pythagorean. I'm sorry, your Pythagorean identities. So those are your Pythagorean identities. Now, the good news about the Pythagorean identities, you don't need to memorize the Pythagorean identities. You're going to have a district cheat sheet for the rest of the year. So for any homework, test, quiz, you will have the cheat sheet available to you. And on that cheat sheet, you have the Pythagorean identities. So you won't need to memorize these. However, it is going to be very helpful for you to understand them very well, like as far as practice, because we are going to manipulate them a lot. So we will do some practice. We're not going to do practice today. We'll do practice when you guys get back. Real quick, I just want to kind of do the understanding of the product or the squared terms. So a lot of people get confused because they think x times x is x squared, right? OK, so why is this not theta squared? Why are you not squaring the theta? Why is the tangent squared? And again, it comes into our understanding of our trigonometric functions. Remember, I related our trigonometric functions to like a square root. If you did 1 plus x, or the square root of 1 plus x times the square root of 1 plus x, that gave you the square root of 1 plus x squared, which just leaves you with 1 plus x. Correct? It doesn't leave you with 1 plus x squared. So what I mean by the reason why I bring that up to you guys is if I'm multiplying the sine of theta times the sine of theta, we got to remember it's the sine of theta, right? Just like it's the square root of 1 plus x, right? So remember, these are angles. So it's very important for you guys to remember this is sine squared of theta, not sine of theta squared. Because sine of theta squared, you're squaring the inside, right? It's sine of an angle. That's very different if you have an angle squared compared to actually squaring the function. Does that make sense? That make sense? We don't square the inside of the radical. We're not squaring the radical, or inside of the radical. So you don't square the angle. It's the function squared. And if you don't like this notation, again, write it like this. That's fine. Mathematically, that's fine. Nothing wrong with that answer. You're just not going to see it as an answer choice, right? Or written on a test like that. OK? All right. So now let's go and move on to the next set. If you guys remember when we talked about trigonometry, we talked about graphing. I didn't make you guys say, hey, guys, you need to know how to graph. But I did say graphing was rather important, though, right? So let's go and take a look at some graphs and see if we can know what these graphs represent. So hopefully, since I told you these are all your, these are familiar to you guys. OK, so at this point, you guys should know what all these graphs look like. hopefully, or what each one of these graphs look like. And hopefully, we can just play a game without looking at our phone and recognize that this is going to be the sine function, cosine, cosecant, secant, tangent, and cotangent, right? Now, when we worked on graphing these functions, one thing that we talked about was symmetry, right? And our most important symmetry that we really talked about was symmetry about the y-axis and symmetry about the origin. Because if you guys remember, if you have something symmetrical about the y-axis, then that function notation, f of negative x, is going to equal f of x. And we called the function even. And in the same respect, if f of negative x equaled opposite of f of x, that means the function is reflective about the origin. The function is what we called odd. So I think the easiest thing when you're identifying symmetry is identify symmetry about the y-axis first. And so let's look at sine. If we look at sine, is that symmetrical about the y-axis? Can you flip it across the y-axis and you get the exact same function? No. So then we say, all right, well, let's check if it's symmetrical about the origin. Can I reflect this about the y-axis and then reflect it about the x-axis? Do I get the exact same graph? Yes. So that means this works, right? Now, let's, instead of using f of x function, which represents any function, let's use that for the sine of x function. That means the sine of a negative angle is equal to the opposite of the sine of that angle. Now, I still think we need a little bit of clarification, so let's double check this. Let's pick a point, pi halves. Hopefully, you guys know from the unit circle, pi halves is equal to 1, right? You can think pi halves, sine 1. You can also see the graph. And then negative pi halves, think about the unit circle, that's equal to negative 1. Now, let's think about this. Is the sine of negative pi halves equal to the negative of sine of pi halves? Does it work? Yes, it does work. So now let's go and look at cosine. And if you guys look at cosine, you can see that cosine is symmetrical about the y-axis, right? So therefore, it's even. And if it's even, then that means this works. So cosine of negative theta is equal to the cosine of theta. And again, let's pick a point on this graph to make sure that that works. Let's pick pi. If you guys think of pi, that's negative 1. If you think of negative pi, that's also, negative 1. So is the cosine of negative pi equal to the cosine of pi? Yes, because it's even, right? So you guys can see how these work when you're not looking at your phone. Now we can look at the rest of these and just identify what their identity will be just by looking at the graph. So you can see here, this is symmetrical about the origin, so therefore cosecant is also odd. You can see secant is even, so therefore that's also, that's symmetrical about the y-axis, so secant is also even. Tangent, if you flip over the x and the y, you can see that's odd. So therefore, I can write it like this. And cotangent is a little bit hard to do with just one period. That's why I represented it as 2 periods. But you guys can see if you flip this about the y-axis as well as the x-axis, do you guys see how you get the same graph? But I had to do 2 periods for this instead of just 1. But this one's odd. So you're like, wow, Mr. McLogan, that's a lot of things now to remember. You're right. It kind of is. But the easy way that I kind of think about this is the only functions that are even is cosine and secant. Every single time you're taking the trigonometric function of a negative angle, it's going to give you the negative result of that angle, except for cosine and secant, right? So I really just kind of focus on these, remember these. Oh, if it's cosine and negative angle, that doesn't change anything. It's still this cosine of theta. And same thing with secant. The rest of these, I just know it makes it negative, OK? And these are what we call our even and odd identities. OK? All right. So now the next one, which I'm going to play around with on I'll play around with on Desmos so you guys can kind of visualize this. But I just want to kind of fit them in here. And let's just kind of take a look. Let's just focus on, here, let's just do one period here. OK, so my question is, here's like the main question. Is there a transformation that we can apply to all the trigonometric functions that gives them another function? Now, we have some constraints here. Remember, we only have transformations that we talked about is stretching, compression, vertical stretch, vertical compression, horizontal stretch, horizontal compression, reflection of the x-axis, reflection of the y-axis, horizontal shift, and vertical shift, right? And you guys would agree with me. It doesn't matter what transformation you apply to sine. You're never going to get the graph of cosecant or secant based on those transformations, right? Whatever transformations you apply to sine, you're never going to get cotangent or tangent. Yes? So sine can only look like cosine. Cosine can only look like sine. Same thing. Cosecant's only going to look like secant. Secant's only going to look like cosecant. Tangent can only look like cotangent. And cotangent can only look like tangent. But again, my question that I'd like to draw up to you guys, can we apply a list of transformations that will work for every function? So that means whatever transformations I apply to sine, that gives me cosine. Whatever transformation I give to cosecant will give me secant. For tangent, gives me cotangent. OK, so let me start you off. If I wanted to make sine look like cosine, isn't the easiest operation, all I have to do is just shift sine pi halves to the left, right? Because that's at pi half. So if I just shifted it pi halves to the left, I get cosine, right? So that works. The problem is, if I separate cosecant to the left pi halves, I get secant, looking good. The problem is if I shift tangent pi halves to the left, or if I shifted it to the right, it doesn't matter, I'm not going to get the cotangent function. Those look completely different, right? Shifting is not going to make these look the same. Would you guys agree? So shifting pi halves to the left or right, whatever, a distance, doesn't work. So I just want you to think about what would something do. And it might be helpful to do this, to think about how could you transform tangent so that it looks like cotangent. And remember, just a little FYI, this is at pi halves. Flip it about what? What does the y-axis work? No, I'm just asking. It doesn't matter. At least for this one, right? Because it won't matter. If you think about this, reflect off the x or the y, and the reason being, it says odd, right? It's symmetrical about the x and the y-axis together. So if you reflect over one, it's going to look like the reflection of the other. So that's why I was just bringing up that question. It doesn't matter. But let's just go with the y-axis, all right? OK, so but if I flip this over the y-axis, it's still not the same, though. What do I need to do? So I need to flip it and then shift it. You guys agree?
You could do that to all of them.
And then let's see if that works. Let's look at this one. If I flip this about the y-axis and then shifted it over, would it now give me the cosine graph? Yes, it would, right? So let's take a look at this. We could basically say if I took the sine of x and I flipped it about the y-axis, and then I shifted it pi halves to the right, right? But again, we got to be careful, though. That's actually not shifting it pi halves to the right, right? Or to the left. Because in this case, actually, that's not represented left. That's not actually shifting it to the right pi halves, is it? So what we'd actually want to do is if we wrote it like this, then if we needed to subtract it out, oops, what am I doing? That would be the correct transformation. OK? So, however, we're not going to write the transformation like this. We're going to write it like this. And actually, we're not going to write it with negative x plus pi halves. The way that this identity works is we actually write the pi halves first. So the function is sine of pi halves minus theta, I'm using theta instead of x, is just equal to cosine of theta. And the cosine of theta, cosine of pi halves minus theta is equal to the sine of theta. And the tangent of pi halves minus theta, what can tangent look like? What does tangent look like? Does tangent look like secant? Cotangent. Oh, and I forgot to mention, but again, this works, and I'll show you guys on the computer as well. But this works from sine to cosine as well as cosine to sine. And then cotangent is pi halves minus theta equals tangent of theta.
For this, why wouldn't we make theta positive? Like, why wouldn't we get out the original data, factor out the negative, and make the theta minus?
You could. I mean, there's nothing wrong with writing it like this. There's nothing wrong with that. And when we were graphing, that would be our typical preferred method, right? I'm just telling you the way that you're going to see these represented, the way that they're in the problems represented, is like in that format. Okay? So therefore, tangent, and then we have cosecant. And what graph does cosecant look like? Secant. So you might say, Ms. McLogan, this is a lot of things to remember. And yeah, I mean, it is. But the way that I kind of like remember these is, again, I just think of the graphs. Like cotangent looks like tangent. Sine looks like cosine. Cosecant looks like secant, right? So as long as I'm not confusing what the graphs are, then those are rather easy to remember. And again, when you look at these, I think of these as like transformations. I think of these as like even and odd. So I know that those are the only even ones. The reciprocal functions and quotients, I can think of x and y's in case I get confused. And the Pythagorean theorem, those are going to be always given to me, so I'm not concerned about memorizing them. OK? Whew.